Okay, so hey everyone, today I'll be doing the week 8 physics video. So first we start with the question 1. Which of the following are true about the energy transformations in an electric DC motor? Now, the energy source of the DC motor is the electric energy from the battery. I mean, obviously it's a motor, it's going to be powered by electricity. Whenever a DC motor is on but it's prevented from moving, most of the energy is transferred to heat. This isn't physics, it's pretty much logic. Stop a motor from moving, just trap it in. It'll have nowhere to move, so it's just gonna produce heat, heat, heat. And it's not gonna move anyway, there's no motion. Meaning that this whole energy, because remember, mechanical energy will get converted into multiple forms of energy, and thermal energy is almost always gonna be one of them. So if motion isn't into play, يعني mechanical energy is the other is only going to transfer to the thermal energy. An electric motor loses some energy to the resistance of the coil, obviously common sense. The efficiency of a DC motor is always 100%. Now this is not true because basically unless you're taking the most idealist of cases which are very unrealistic, nothing is ever at an efficiency of 100%. So this is wrong. And the source of the DC motor is the energy of the magnetic field. We already said this from the battery, so this is wrong. Okay, question 2. Which of the following will experience a magnetic force? Now for this one, you're gonna have to know two formulas. I believe it was FQV sine theta for a particle or a single charge, and F equals to IBL sine theta for a wire. Now, what we're concerned about is not the Q and the V, and it's not the I and the B and the L. So I don't think they're gonna ask you to memorize these formulas because we didn't take them in the book. But يعني it's how you know. Q and V you don't need them, so you're gonna need the sine theta and the result, which is the force. IBL you don't need it, and you just need the sine theta. Okay, so we start with which of the following experience a magnetic force? A charged wire placed in a magnetic field. طيب تمام. A charge wire placed in a magnetic field. What does this wire do? It's just charged. There's no current. There's nothing flowing. No electricity flowing. No charges. The conditions for a magnetic force to be experienced: the object has to be in motion or the particles. So let's write particles have to be in motion. And two, uh, the sine of their angle has to be greater than 0. Okay, these are, as far as I'm aware, the only two conditions. I think there's another question that clarifies it more. But for this question, this is what we're gonna use, right? So actually, يعني forget about these. Just focus on the 1 and 2. Okay, a charged wire placed in a magnetic field. No current. It didn't say current. Notice here it says current carrying wire. So this is wrong. A current carrying wire moving parallel to a magnetic field. Now, uh, let's pull up a calculator, right? Let's pull up the Casio. No, I don't want to activate. Next. Okay, parallel. So, parallel is gonna be sine 180, right? Because it's moving, or sine 0, I think. Yeah, sine 0, because there's no angle. It's moving like this, right? This here and this here. There's no angle between the two. Where is the angle? There's no relation. So it's gonna be 0 degrees. So you put sine 0, right? 0 degrees will give you a result of 0, right? So anything multiplied by 0. So let's say it said current carrying wire. So we're gonna apply F equals I B L sine theta. Let's say the wire was 2 meters. It had a magnetic force of 45, the magnitude, and the current was 4 amperes. So it'd be 4 times 45 times 3 times sine 0. Sine 0 can makes this 0. So it would be 4 times 45 times 3 times 0. Anything multiplied by 0 immediately gives you 0, so there would be no force. Okay? Now, a moving single charge whose velocity makes an angle of 90 degrees with the magnetic field. 90 degrees, sine 90, you should know this from math. Sine 90 equals to 1. So if anything, right, if it is normal with the field, which means it makes an angle of 90 degrees, it gives you maximal force, because it's going to be 1 times the force. Because remember, the sine of an angle can always never be greater than 1. So it's always less than 1 or equal to if it is 90. So in that case, when it is 90 degrees, uh, we don't have nothing but like a maximal force. That's all I'm gonna say. When you have sine 90 degrees, it's gonna be carrying, it's gonna have like a magnitude, right? But we also have to check for the other condition, which is the particles are moving. So I'm just gonna write sine theta greater than 0. I'm gonna keep these. We know that this is moving. It is a moving single charge. So this condition gets ticked. Okay, and sine 90 is 1, which is greater than 0. So this condition is also ticked, which means that this is the answer. One of the answers. Tamam. A current carrying wire. So current carrying wire, which means that the wire itself maybe isn't moving, right? But the charges are moving, because what is a current? A current is a flow of charged particles. So if you have current, which means you have particles moving. So that's the first condition ticked, making an angle of 180 degrees. Now, if you don't know what sine 180 is, it is 0. However, you have a calculator. Sine 180 equals to 0. Here we said it has to be greater than 0. So this condition is not ticked off. This is wrong. Okay. As you can see, it is very simple. You just need to remember these two. A current carrying wire placed perpendicular to a magnetic field. Remember, perpendicular means normal. This is perpendicular. You have a 90 degree. So immediately we know that it has sine 90 is greater than 0. And it's current carrying, right? Current carrying again means that there's a flow of charges, which means that the particles do move. So this is another answer. That's it for this question. And this will be asked, I believe, 2 or 3 more times. So, yani, this is a very easy topic. You guys shouldn't get mistakes. Consider the diagram from below. This is the diagram. The device shown is a galvanometer. Just memorize it. Is there any other way? Moving coil galvanometer. Just say galvanometer. The device is used to measure a weak current. And which of the following will make this device more sensitive? Now, honestly, this is common sense, right? Adding turns to the coil. This makes it more sensitive, right? Because you're gonna have more coils. Yani the magnet will pass through more. It will measure more current. Using a stronger magnet, again, for the same reason, this is logic. Now, here we're gonna start from the end. Using a coil with less turns. This doesn't make sense because we just said if it adds turns to the coil, it makes it more sensitive. So for using a coil with less turns, it makes it less sensitive. Using a spring with a high spring constant. Now you're gonna see this in a later question. The galvanometer uses a spring with a lower spring constant. This is higher. It makes it less sensitive. Reversing the direction of the magnetic field. This either does nothing or it just makes it yani, less useless. So this is also wrong. Right, these questions so far, from what I'm seeing, they're purely based off logic, other than the memorization question. By the way, there will be a lot of right-hand rules, and I can't really explain them to you. I'll explain the new one, which is about Lenz's law. I'll try to. However, the old ones, you guys should know, they came last week, and I can't really explain them to you because I don't have a camera. Okay, so fill in the drag and drop the correct labels. This here, this circle thing is a split ring commutator, and essentially what it does, right? A split ring commutator makes the electromagnet, this thing here, this in a motor is gonna turn, right? However, you can see from the picture, again, this is logic, you just have to visualize it in your mind. It can't turn the full 360. So what this does, it's every half turn, okay? So like, let's say this was the electromagnet here, okay? And this is the split ring commutator. Every half turn, this would rotate the electromagnet. So this would flip it. So yani it was moving, let's say it was moving clockwise, okay? Up until the 180 degrees at the half turn, right? Then it would flip the electromagnet, it would flip it and make it go counterclockwise. As you can see, this moved 180 clockwise and then it moved 180 counterclockwise, which means it moved a full 360, yani full rotation. Basically, let me re-explain it. You have this electromagnet. Let's say this is the electromagnet straight line. Okay, it moves counterclockwise. It moves clockwise. Sorry, it moves clockwise at the start. You can see here this moved a full 180, which you should know is a half rotation. It's a semicircle. A circle is a full rotation. A semicircle is a half rotation. Now, because of يعني when you visualize it, you're gonna see that it's not. It doesn't make. It can't. It can't. It literally can't. Or if it can, it is gonna be very hard to continue this rotation to a full 360. What instead is way easier to do and is very easy to visualize in your mind, it simply flips and rotates the magnet in the other direction. So this was going clockwise at the start, this would be going counterclockwise. Now this went 180 degrees clockwise, it's gonna go 180 degrees counterclockwise, which means it goes the full 360, which is one full rotation. Okay, that's what the split ring commutator is. The other thing is the brush. Just memorize it. There's only two blanks anyway, so خلاص, it's the brush. By the way, these brushes are made of carbon. Keep this in mind. I don't know if they'll ask you it, but just keep it in mind. The device shown in the diagram is the electric motor. Obviously, this is the DC motor. خلاص, that's all you need to know. تمام. If the current is turned on when the coil is shown in the diagram, the coil will rotate counterclockwise. Okay, this is a mixture. You can either memorize it or you can apply the right hand rule. I can't really يعني, show you guys the right hand rule because again, I don't have a camera. Ask your teachers about it if you don't know it, but this is the easy right hand rule. The brushes of the motor are made of carbonate. In the next question, they asked what I told you about. So, yeah. Question 6. A single charge is moving with a constant velocity v in a magnetic field B. Rank the magnitudes. Okay, this is an application of the thing F equals QV sine theta. Now you can do right hand rules here and see. No, it don't even show it. Just show you the direction. So don't do the right hand rule here. We don't need the Q and the V again. We just need the sine theta, right? For the strongest one, sine theta is gonna be equal to 1 for the strongest for the strongest magnetic field or the strongest force, right? Because again, sine theta gives you sine 90 gives you 1. So when it is perpendicular, it gives you maximum because you'll be multiplying it by 1. Meanwhile, for example, if you were to do sine 70, يعني it would give you a number less than 1. It might give you 0. I don't know, 8. So basically, instead of multiplying it by 0.8, which make the number smaller, you're multiplying it by only 1, right? You're multiplying it by itself, so it would give you the maximal output. Okay, let's see this. Here, this looks like, let's start with the first diagram. This looks like it's, like 30 degrees maybe, right? So what this is gonna be greater than sine theta to be 0, because this is let's say this is 30 degrees. Sine 30 is 0.5, right? So this whatever you get from F equals QV sine theta, you multiply it by 0.5, or F equals QV, you multiply it by 0.5. Okay, we're just gonna compare the signs. We're gonna approximate yani. This here, as you can see, it makes 90 degrees. Yani you draw it, this gives you 90 degrees. So sine 90 equals to 1. And again, this is gonna give me the greatest maximal output you can get from يعني a magnetic force, like from the force. So this is immediately 1, right? I don't have to worry about this anymore. I just have to compare this one and this one. Okay, I have the sine value for this one. I approximated it to be 0.30, which is 0.5. Here, this is parallel, right? This is no relation, so the angle is 0, so sine 0. Sine 0 equals 0. Now, obviously, 0.5 is greater than 0, meaning that this is the second one and this is the weakest one. That's it. Question 7. The diagram below shows the direction of forces. Now, there's two ways to apply this. There's Fleming's left-hand rule and there is the right-hand rule we took. Honestly, Fleming's left-hand rule works better in some cases. The right-hand rule works better in some cases. They're both the same, except one's on the left hand, one's on the right, and one uses they're basically the same thing. Basically the same thing. Calls. Look up Fleming's left-hand rule. If you find it works better than the right-hand rule, use it because they use it in the IG textbook for the physics. If you find the school's right hand rule more useful, use the school's right hand rule وخلاص. Whatever works for you. So uh let's try to do it. Okay, I'm gonna do the school's method. The current is your thumb, and for we're working on this one by the way. Here, the current is your thumb. So point your thumb in the direction of the current. Now, the magnetic field is your second finger. So we're gonna orient it like this. We're gonna orient it يعني this way. This your the finger next to your thumb, right? Is supposed to go in the direction of the arrow I drew. Okay, extend the third finger out. You'll find the force going down. However, you can't like draw downwards in يعني a 2D scale. So what you're gonna do is you're gonna write into the plane. However, physicists don't do that. They write this. This means into the plane. Okay. Yeah, this is just an application of the right hand rule. Now, how do you know if يعني say you found it, right? And say you forgot if it's into the plane or out of the plane. What does that mean? Imagine it like an arrow, okay? Here at the base of the arrow, you'll see the X. Okay, at the top, you'll see the tip, the point. So this is how you know. This is actually what they use, by the way. The cross is used to denote the base, and the point is used to denote the end. Okay, so now that we have that, we're gonna erase this. We're gonna do the second one, this one. Okay, current is going straight up in the direction of this arrow. So orient your thumb up, not up like towards you. I mean up as in a straight line. Okay, now this magnetic field is going out of the plane because remember the point here means out of the plane. So what we're gonna do, we're gonna put the second finger next to the thumb in our direction. Again, this is on your right hand. So you extend your finger to the direction that is facing you, to your face basically. Okay, that leaves the force from يعني from what I'm doing right now. It goes to the right, which is accurate. This is correct so far. This is correct so far. Okay, we do the third one. Now, current is going into the plane. So you orient your finger basically down, away from you. Okay, now the current, or sorry, the field is going straight. So down, your finger goes straight, right? From what I'm doing right now, I'm feeling that I'm not feeling actually. يعني I'm seeing that my force definitely goes in this direction on my hand at least. Again, يعني I can't really show this to you. It's a right hand rule. I'm trying to explain it to you the best possible. I possibly can, but I can't do that when I don't have a camera. So from what I'm seeing, yes, this is correct as well. Which only leaves this question, this one. يعني you solved it by trial and error. You can also solve it by testing it out as well. So we'll test it out. يلا. Current in a straight line. So orient your thumb in a straight line basically. Field goes out of the plane. So point your second finger towards you. Now that leaves the force, and if from what I did it, the force would actually be going this way. Okay. However, they wrote it wrong. They said it's going this way. And I don't know if you noticed this picture here, this one, the one that is wrong, is exactly the same as this picture, the second one. However, they only flipped the arrow's direction. The arrow's direction is going this way to the right, and that's what we found. So obviously, if this one was right, and these two conditions are the same, look, B is the same way out of the plane, I is the same way going straight, then how could this one be right and how could this one also be right? Yani it's obvious. There's three different ways to solve this problem from what I saw. Okay, question 8. A magnet is inserted into the loop shown below. The magnetic field of the magnet is directed into the plane of the picture. Okay. Now, if it's inserted, right, if the magnet is inserted to the loop will try to push it back out. Okay, what that means is it is gonna go in the opposite direction of the plane. So here this is going into the plane. As you can see, there's the cross. We want it to go out of the plane because it's the opposite. This is what Lenz's law is. Lenz's law, as a very quick summary, Lenz's law is the EMF going in is going to be the opposite. I don't really know how to phrase it right. It's going to be shown in the last question of this quiz and even before by a bit. But basically, whatever is happening inside, whatever is going to happen, the result is the opposite. Okay, so what it's going to do here, They said it's inserted, which means it's going in. Okay, like this. What we're gonna do, we're gonna try to force it out, which means that we're gonna go instead of we're gonna go in the opposite direction. Here of the magnetic field طبعا. Here the magnetic field is into the plane. What is the opposite of the into the plane? Out of the plane. So we point our thumb towards us. This is the other right hand. This is the same right hand rule essentially. Point our thumb towards us. Then curl your fingers, right? Curl them fully to make a thumbs up in this case, because your thumb towards you means out of the plane, which makes a thumbs up. Curl your fingers fully, you will find that they go counterclockwise. So CCW. Well, I'm not, you write down counterclockwise in the written part or whatever. Okay, that's it. Now, the principle used to determine the direction but not the magnitude of the EMF induced is Lenz's rule, and the magnitude can be determined by Faraday's law. By the way, for Faraday's law, it is negative, or sorry, let me say it, induced voltage, so EV equals to negative d phi by dt. This is phi. Okay. Uh يعني basically it's the derivative of phi with respect to time. Phi is the flux. This is the flux. I don't think they'll ask you that much about it. يعني I think they just want you to know the rule, because it's very weird. There's no way they'll ask you, but just know it. يعني maybe in case it comes. Another way to know it, by the way, is I don't know if I added it. It was negative delta phi by delta time. Another way is negative. Literally, just add the delta sign, because this is essentially what the derivative is. It's the change. Okay, this is Faraday's law. That's it. But I highly doubt that you'll need to know it. It just basically all you need to know, from what I assume, is you need to know the numbers, the magnitude. Okay, this is an application of Faraday's law. The induced current flows from point P to point A. The area is decreasing here. This is what my teacher told me. The area is decreasing here, right? So it's going, because again, you're measuring in this sense, which means that it's going negative. Here, even though you don't need to know that, بس يعني just keep this in mind. The current, if this is flowing like this, the electrons or the current will always flow opposite, because this is the velocity of the electrons, this is the velocity of the charged particles. Now, the current always flows in the opposite direction. So here it's going, if you continue it, it's going to go from A to B. We want it to go from B to A because that's what the current is. It's the opposite. So from B to A. خلاص, that's it. Now, here, this is the graph. I don't know what is this symbol, but I'm not assuming we need it. يعني I highly doubt. What they did again, it is negative delta phi over delta t. I think this is small phi. Yeah, I think this is small phi or capital phi. I don't really know. Whatever. So here it is 30, right? Negative. This is time. Time wasn't given, so we're just gonna use this number. Negative this, negative 30, and this is your answer. خلاص, that's it. Question 10, and I think this is the most we're gonna need to know about Faraday's law as for this year. A rectangular wire is connected to a galvanometer that measures induced EMF. The wire is rotated at a constant rate inside the horseshoe magnet as shown below. How can we increase the EMF? By rotating the wire faster. Now, another way of saying it is essentially this way here. Let it load like this. Okay, this is also testing out Faraday's law. So I will do this. Okay, now Faraday's law and whatever the factors that induce the EMF. Here they say rotating the wire faster. طيب, okay, تمام. Let's test this. Here I'm rotating it slowly. Look at the current. Look at the voltage. It's not going that fast, right? You can see here it's not going that much. However, watch as I rotate it like actually quickly. Look how much it expands to. It expands more. As you can see, the faster I go, the more it expands. Okay. Anyway, let me increase it. Right? Let me increase the coils just so I can show you better. Here, first of all, you notice with the same speed I'm rotating, I'm getting more voltage. So the more loops, right? The more loops I'm getting is giving me more voltage. As this was in a previous question. here the greater the loops, the more loops, this makes it basically more sensitive. The more the thing, the more the voltage. Also, I can increase the strength of the magnet. Huh, 100%. You can see it's giving me more. Yeah, this is just a demonstration of everything that's been asked of me so far. Okay, now let me test to see less loops. Or actually, let me stay because I haven't tested the speed. The speed were more loops. Look, يعني to make it, يعني show you the greater difference. This is normal speed, right? This is my speed here, going slow, taking my time. Okay, if I were to go very fast, look, it would go towards the ends, which means that the speed affects it. By rotating the coil fast, I can also rotate this. By the, I don't think I can move it. I can't move the coil, so I can. Wait. Yeah, if I move the coils, as you can see, it moves faster. This is what they're saying here. This is essentially this exact question. Copy paste. Okay. Which of the following are true for a galvanometer? Basically, what we're gonna do now. The galvanometer's loop must be placed in a radial magnetic field. Okay, memorize this. A magnetic field induces the torque on the current carrying coil of a galvanometer. This doesn't really need explanation. Basically, when you have a current carrying coil in a galvanometer and you have a magnetic field and you rotate this essentially this, you can see here there's gonna be like a moment. There's gonna be a torque. A torque is a moment, as you know. So, هيك look, I'm making moments here. خلص. The coil of a more sensitive galvanometer contains a spring with a smaller constant. They asked this in a previous question. I told you it would have a spring with a smaller constant. This is very important. So always choose this. Now, the greater the magnetic field the galvanometer is placed into, the less it's sensitive it is. You just saw it would give me more, strength in terms of voltages. So this is correct. This is actually, no, wait, sorry, this is wrong. Uh, this is wrong. The more terms a galvanometer has, the less sensitive it is. I just showed you this. It is wrong because the more coils, it's actually the more sensitive. A galvanometer's loop must be placed. We said this. We said the correct answers. خلص. Okay, so question 12. A coil of 10 turns is connected to a galvanometer as shown below. What happens if the north pole of the magnet is inserted through the coil? Now the clip corrupted a bit, so I'm redoing these. I don't know if I showed the experiment earlier. I'm positive I did. Right, the experiment with the Faraday's law with the current, and here there was the coil, and there was the magnet here, and there was the voltage here. This is the voltmeter. You saw that whenever I put in the magnet, right, I had a current, and you know that the voltage and the current are directly proportional, which means that there is a constant K. In this case, it's going to be the resistance. I'm not going to go into proportionality. You guys know this. Basically, if I'm reading a current, I'm reading a voltage. If I'm reading a voltage, I'm reading a current. So here, when I put the magnet in through the coils and I kept turning it, we saw there was a voltage being read, which meant that there was also being a current. So when the magnet is inserted through the coil, a current is being read by the galvanometer. Question 13. The direction of the current in the loop according to Lenz's law is counterclockwise. Now, I think I explained this previously, but basically, pushed in, okay, the direction, the thing, the actual magnetic field will try to oppose it, right? By going into the opposite direction of the field. Here you see that I have an X, okay? Which means it's going into the plane. What I wanted to do, since it's going in, this you can see it's going in, I push it out, right? They're opposite directions. So I want to go in the opposite direction of the field, of the plane. Right, which means that if this is into the plane, I'm gonna go out of the plane, and out of the plane is the thumb pointing towards me, my thumb. Then I curl my fingers. When I curl my fingers, I see that my thumb is going counterclockwise. My fingers are going counterclockwise, sorry. My thumb is pointing towards me, because again, out of the plane means pointing towards me. So my my fingers curl. I'll find it that they're going counterclockwise. Now I explained this in more in detail in question 20. So just, yani, this is when I'll explain it in detail, but this is basically a summary. Question 14. Okay, remember for this one, we said two conditions. One, particles move. And two, sine theta is greater than 0. Okay, here, a charge that is stationary. Stationary means not moving. So this condition is not fulfilled. Immediately, no force. A charge moving, so it is moving, and at an angle of 30 degrees. Sine 30 is 0.5. which is greater than 0, which means that sine theta is greater than 0, which means that we have force. Okay? Now, a charge moving in the direction, so we have moving in the direction opposite to the magnetic field. Opposite means it is 180 degrees, right? Because this is here, let's say this is here, this is your field, or B here. The charge is here, let's say call it C. You can see there's a 180 degree, right? Sine 180 is equal to 0, which means that the sine of theta is not greater than 0. So this experiences no force. And this is question 14. Question 15. Okay, this is the right hand rule that can also be used as Fleming's left hand rule. Point your thumb straight in the direction of the current, because the current is going straight. Uh, the magnetic field is going into the plane, so I direct my second finger into my tablet or into my laptop or whatever I'm using, into the plane. So then I extend my force, I extend my third finger to indicate the force, which is going leftwards. This. So basically, let me recap. Right? Current is my thumb. My thumb extends straight because as you can see, the current goes this way. Okay, Q is the current in a single particle. يعني it's the charge بس يعني for simplification purposes. This arrow for simplification purposes, do not write this down in the written, is the current. So I put my thumb in that direction. The plane is into the plane. So I put my thumb, or not my thumb, sorry, my second finger into the plane, which is essentially my tablet. My plane is the tablet or my laptop or whatever I'm studying on, into it, right? I'm pointing it into it, right? I extend my third finger, which indicates force. I find that it is going leftwards, and that's why I put leftwards. Okay, question 16. Now, for an AC, for the AC circuit, right? This is the graph. It's sinusoidal, so it's like this. Okay, you can see here I have a positive value and a negative value. Mathematically, it's going to be very annoying to calculate like this. If I have negative, then positive, negative, then positive. Okay, what is much easier to do is I calculate the RMS, which is the root mean square. So this is a current. Here is time. In the root mean square of current, even in voltage, by the way, I'll get to this now, is the peak current or the max current, let's call it IP for peak, and divided by radical 2. Same thing for the VRMS, so VP over radical 2. This is your formulas. Okay, now we don't need the voltage, they're not asking for it, they're asking for the current. Tamam. IRMS equals to, here it's 20 milliamperes. We want our answer in 20 milliamperes, so we keep it 20 over radical 2. This gives me 14.1. Question 17. A magnetic force acts on charges only when those charges are moving. I explained this. So a stationary charge experiences no force. This is something you have to know. And again, it got applied 2 questions before this. A magnetic force exerted on a current only if the current is not parallel to the magnetic field. Because remember, not parallel or parallel like this has 0 degrees. Sine 0 gives me 0. So it would give me no force. Yani there would be no force exerted. And the magnetic force has a maximum magnitude if the current is normal to the field. Again, y sine 90 equals 1. So I'm not like reducing it by anything. I'm not reducing it by a factor of like 0.5 or 0.75, for example. Okay. Question 19. A current is induced in a circuit when magnetic flux changes. This is Faraday's law. Induced current or anything induced voltage. Because again, if you're inducing voltage, there's going to be a current. D phi over dt. Phi is flux, right? So and the derivative is a rate of change. So when the flux is changing, which is what the d phi over dt means, you're gonna have an induced current or an induced voltage. Which direction? Okay, here same example for as every other thing in Lenz's law. Pushed in, it's gonna try to push it out. Here it's going into the plane, so it's gonna go the opposite direction. since it's gonna try to push it out, which means it's gonna go opposite, which is out of the plane, which is my thumb pointing to me. I curl my fingers, it goes in the counterclockwise direction. So, what is the direction out of the page? As I said, because it's the opposite. And by the way, maybe they told you it was being pushed out, right? It will go in the same direction as the plane. So here, for example, let's say this was being pushed out. Let's remove this. Okay, let's remove this. Let's say they do it like this, pushed out. Okay, what I'm gonna do now, if it's pushed out, it's gonna stay in the same direction. Okay, same direction as the magnetic field. So I'm gonna point my thumb down into the page, and then I curl my fingers. It will go clockwise. Okay, I when curling my fingers, it goes clockwise. Basically, somebody, right, pushed out,